Hey, how's it going? Looks like I've completed all of the easy problems on Leetcocde, so let's take a look at some medium problems. We can look for the easiest ones, so it should go pretty fast, I think. Okay. Now that's weird. I thought I sorted... Okay. Alright. Print immutable linked list in reverse. So let's see what this one is. You're given an immutable linked list. Print out all values of each node in reverse with the help of the following interface. Immutable list node and interface of immutable linked list. You're given the head of the list. You need to follow the function to access. Print value, get next. What? Okay. Get next. N equals head. Well, N is not nunt. N equals N dot get next. This is pretty easy here. I can see why this has such a high pass rate. Okay, print value. I guess this has to go below. Okay, oh, we're supposed to do it backwards, huh? It says in reverse. It said in reverse. I was not paying attention. All right. New plan. Oh, right. Yield recursion. None type has no attribute. Print value. Well, that sucked. Okay, let's try another one. Wait, I kept the tab open deliberately. Guess what number using bitwise questions. There's a number n that you have to find. There's also a predefined API int common set bits, which returns the number of bits where both n and num_i are 1 in that position of their binary representation. In other words, it returns the number of set bits in n and num, where n is a bitwise and. Return the number n. Okay, how big can the number be? Oh, quite big. Quite big. Okay, 2 to the 30th. So b equals 0, bit equals 1, while bit is less than 1 or 2 to the 30th. So we will say b times equals 2, or you could do it like this, I guess. All right. So if common set bits of b, then v plus equals b. And then everybody's happy. All right. I'm sure that there was a more efficient way to do it, but whatever. All right. Back. Okay. Dot product of two sparse vectors. Assuming I know what a dot product is. Well, I did do the machine learning course. Okay. Given two sparse vectors, compute their dot product. Implement sparse vector. Initializes the object. Vectors nums. Dot product is vector. Compute the dot product. Alright. So 1 times 0, 0 times 3, 0 times... Okay. It's pretty simple. I guess I did know what a dot product was. Alright. Self dot a equals nums. Alright. So nums 1 dot length equals nums 2 dot length. Return sum of something for I in range length self dot a. No, let's not do it that way. I don't want to do it that way. That's dumb. I times j for I comma j in zip self dot a. This is how you're supposed to do it. Vec dot a. All right. Run. Okay, that is awesome. Let's take a look at the next one. Minimize product sum of two arrays. The product sum of two equal length arrays, A and B, is equal to the sum of A times B for all. What? That's just the dot product again. Given two arrays, nums1 and nums2 of length n, return the minimum product sum if you're allowed to rearrange the order of the elements in nums. Now that is fascinating. Do we just want one sorted and one reverse sorted? Is that the minimum? There are no zeros. Well, you know what? I think that might be it. So we'll see if it doesn't work. Sum of I times j for I comma j in zip nums1. Sorry. Sorted nums1, comma, reversed sorted nums2. Okay, we'll see. I mean, that seems intuitive to me. Maybe it's more complicated than that. All right, sweet. Okay. Maximize number of, close tabs to the right, number of matching indices after right shifts. You're given two integer arrays, nums1 and nums2 of the same length. And index I is considered matching if nums1 of I equals nums2 of I. Well, that does make sense. A right shift is defined as shifting the element at index I to index I plus 1 for all indices. Okay, so basically they're saying if you push it from left to right, then yeah, okay. Thinking. Oh, you know what? Look at these lengths. We can brute force this. All right. So we'll say for shift, it doesn't matter which one we're shifting, in range length nums1. Okay. And then CNT equals 0, and we'll say max equals 0. Then we'll say for I in range length nums1, any number of right shifts on num1. So we have to push nums1 further, right? Yeah. Thinking. So I really think that we should be comparing the length of nums2, and then adjusted digit equals, it would have been the original place, but we have offset it by s, right? Now, if AD is less than length of nums1, no. If AD is greater than or equal to the length of num1, then we break. Otherwise, if nums1 of AD equals nums2 of I, and CNT plus equals 1, then when we're done, m equals max of m comma CNT, return m. I mean, sometimes brute forcing is just the easiest way, except when it gives you the wrong answer. That's that is something. Oh, you know what? Oh, I did this completely wrong. AD should be the position in nums2. Any number of digits. So you wouldn't want to push it further. Okay, let's do it without the bit shift first, and then we can make the adjustment. So we're going to say for I in range, max length nums1, comma, length nums2, right? And then CNT equals 0, and if nums1 of I equals nums2 of I, then CNT plus equals 1. Yes, but we want I1 I2 equals I comma I, right? I1 and I2. Now, if I1 is greater than or equal to length of nums1, then we're going to break. Let's not break, let's continue. Or I1 is less than 0. Or I2 is less than 0. We're going to have full freedom however we want to adjust this. All right. Then we go there, and when we're all done, we say m equals max m comma CNT. But we're going to say for offset and we want to push this one. Indeed. That's annoying. Return the maximum number of matching indices after performing any number of right shifts on num1. If we shift enums1 to... Oh, it loops back around? Nobody told me it looped back around. And they're the same length. Nobody told me it looped around. And they're the same length, so... yeah. Just thought it was going off into the void of space. Well, that's why you get your requirements straight. Well, that sucked. Okay. Permutations 3. Now that sounds scary. Given an integer n, an alternating permutation is a permutation of the first n positive integers such that no two adjacent elements are both odd or both even. Return all such alternating permutations sorted in lexicographical order. All right. Such that the first n positive integers such that no two are both odd or both even. All right. Okay. Build. Yeah. Is odd. Okay. Group 1, group 2. Assert G1 or not G2. If not G1, then return. Otherwise, current return p dot append c, then return. Otherwise, c dot append. Well, we have to do every single one of them. So, how are we going to do this? Y in range length G1. G1 copy equals G1 dot copy. G1c dot pop I. Yeah, and then we're going to have c dot append like that. Right? And then build G2 comma G1c like that. So we'll say odds equals I for I in range length of 1 to n plus 1 if I mod 2, and evens is I for I in range if I mod 2 equals 0, right? Then we just say build odds, evens, and evens, odds. And return, oh, no, wait, we can't do that because they have to be sorted. Sorted in lexicographical order. Is it possible they're already in lexicographical order? I think so, because we start from the bottom and then we build up, right? No. Required positional argument missing. I do not believe that they are in lexicographical order. We're going to have to figure out how to put them in lexicographical order, aren't we? Mm-hmm. Okay. I think that's fine. Let's put these in lexicographical order. P dot sort key equals lambda G what the hell? Dot join G, I guess. Expected str instance int found. Annoying str of I for I in G. Okay, I was expecting that to work. Oh, look at that. Oh, that is not good. Oh, that is terrible. Oh, this is very unfortunate. Okay. Just to be clear here, the thing that we append p.append c. Oh. C equals C dot copy. That was pretty dumb. Okay, 1, 2, 3, 4, 1, 2, 4, 3, 2. That is very odd. Very odd indeed. G1C dot pop I, right? How can it possibly be getting a duplicate? One, 3. Okay, let's figure out which one it is adding duplicate. 1, 2, 4, 3, 2. One, 2, 4, 3, 2. So it is adding 2 twice. I have to look at what it's doing. Print G1, G2 and C. Okay, 1, 3, 2, 4. Yeah. 2, 4. So I got the 1, got the 1. Look at this. G1C dot pop I. See, it's removing it. The only thing we add to C is something that. Did it have a duplicate to begin with? One, 2, 3. 1, 2, 3, 4. Okay. 1, 2, 4. I don't know what to do. I cannot see where this is screwing up. It must be some sort of a stupid mistake. C equals C dot copy. That's it. That's it. Cn equals C dot copy. Cn dot append. Yeah, the fix wasn't a fix. Two, 1. Should have been 3. Should have been 3. Yeah. Okay. If not G2. Man. Oh. What a stupid mistake. Okay, now I see what happened. I see what happened. It was, this was not. Yeah, the range is 1 to 10. That one was just kind of silly. I'm not upset about that. All right. And it passes. Whew. Okay, let's hope the next one is better than that. That was... Clone an array trait. You see, that just doesn't sound fun. Number of unique categories, split binary search tree, design an expression. None of these sound fun. Oh, whatever. Clone an array tree. Okay, given the root of an n-array tree, return a deep copy of the tree. Each node of the n-array tree contains val and a list of all of its children. That makes perfect sense. Okay, so yeah. We'll have node and, I don't know, new tree or something like that. All right. It's almost like we need the parent nodes, right? Fake head original equals node, right? fake head original node, and then children equals root. Okay, so that defines the original one, and then fake head new equals node, like that. So if we're passing the parent, then we should be able to, I think this will work. So we'll say for K, for kid, in children, and then t.children.append node val equals k.val. Is that it? I think so. And then the recursion step is k and t dot children -1, like that. And then if there's no children, then we stop. Then we just call this fake head original and fake head new. Return fake head new dot children 0. Children is not defined. For k in n dot children. All right, sweet, it worked. None type object has no attribute val. Oh, so it's not an empty. Why is there a none? All right. If n dot children is none, then return, I guess. If k is none, then what? Why is there a none? There shouldn't be a none. Then t.children.append none, I guess. Else, it's just got really dumb. All right, that made no sense at all. I'm now mildly annoyed. Okay. All right, clone and array tree. Guess the number. Snaps to the right. You know that this was a recommendation from me. I made it to Firefox because there used to only be like close to the left or close to the right. I don't remember which it was. Whatever it was missing. But I'm like, hey, now that it's nested, could we add all three? Okay, close tabs to the right. Oh, my air quality just got bad. I don't know what that's about. Well, whatever. There's a number n between 0 and 2 to the 30 minus 1, both inclusive, that you have to find. There is a predefined API, bits in common, that helps you with your mission. But here's the challenge. Every time you call this function, n changes in some way. Keep in mind you have to find the initial value of n. Calculate the count, which is the number of bits where both n and num have the same value. N equals XOR num, return count. In this world, all numbers are between. Thus, for counting common bits, we only see the first 30 bits of those numbers. All right. Every time you call the function, changes in some way. Well, in what way? Common bits acts as follows. Calculate count, which is the number of bits where both n and num have the same value in that position of their binary representation. N equals n XOR num. Okay, so it's exactly the same as before, except it's doing this dumb XOR thing. So let's see if I can get my code from earlier. All right. Submissions. All right. So we have our code from earlier. Common set bits. It's just common bits. Two less than 2 to the 30th minus 1. 2 to the 30th minus 1. B is lesser than or equal to 2. Okay, n equals n XOR num. So by calling it twice, we should be undoing it, right? It seems like this should be working. Yeah, I mean, if you run XOR twice, then you end up back where you started from. So, common bits. You have to find the initial value of n. Oh. Okay, that was pretty stupid. Yeah, return count. Print X. Print Y. Okay, am I confused how this works? 15 XOR 15 is 0, right? Yes. Now, 1 XOR 32 is 33. It almost seems like it's taken like the complement or something. X comma Y comma B. Yeah. 1, 2, 4, 8, 16, 32. 24, 25, 24, 25. And the number is 31, right? Which should be every single thing up to here. 26, 25, 26, 25, 26, 25, 24, 25. Number of bits where both N and M have the same value in that position. Okay. So if it if Y equals 25, print X comma Y comma B. Pissing me off. Maybe we don't want, maybe we want the first one. If okay, baseline equals common bits of 0. If X equals baseline plus 1, there we go. Yeah, I was going to get a beer. Maybe I need some scotch. All right, you know what? I think that's probably enough. All right, see ya.